Hello, and welcome to this lesson on multi-threaded programming. This lesson begins with a brief review of parallel programming in general, and moves on to discuss multi-threaded programming in particular. It uses the POSIX threads library as the canonical example, though the same principles apply to most all threads libraries. To motivate parallel programming, consider the following task. You are given a set of web pages, some of which link to each other. We'll draw this using the standard abstraction of a directed graph where outgoing edges represent links. So web page A here contains a link to web page B. And our goal is to figure out how many links our website, say U, has pointing to it. This is something that a search engine might do to help figure out how popular a website is. Now there's no way to know whether another web page has a link to our web page in it without looking at it. So, in one way or another, we're going to need to read all of the web pages in our collection. And if we try to do this with a single processor, this could take a long time. First, I have to read web page A, then web page B, etc. Thankfully, this task is highly parallelizable. That is, there is nothing about my processing of A, i.e. counting how many links it has to website U, that affects how I'm going to process website B or website C. So, I can easily divide up the web pages among, say, 3 CPUs. Let's give these over here to CPU 1, these to CPU 2, and these to CPU 3. Now we can let each CPU count up in its subgroup how many links it has to U, and then we can just add these numbers up to get our final answer. Returning to our time graph, we see that with 3 CPUs, we only need 1/3 of the time. Potentially, with n CPUs, we would only need 1/n of the time. It is important to realize that we're doing the same amount of work here. Suppose that in our original thread, we first process the websites assigned to CPU 1, then those assigned to CPU 2, and then those assigned to CPU 3. Well, in parallel programming, we've cut this one long strand of computation into 3 shorter strands and arranged them in parallel by giving them to 3 separate CPUs. This, of course, is the ideal case for parallel programming. Now, of course, in real life, we don't always get as many processors as we want. They aren't always available. And given that our application will likely be running on the same machine as others, we don't know exactly how many processors we will have access to. But by expressing our algorithm in this way, we can take advantage of the processors we do have, and thus make our algorithms run faster.